Youngs Modulus, otherwise known as the tensile modulus, is a measure of stiffness of an elastic material. It's also a quantity we can use to characterize these materials. It's defined as a uniaxial stress divided by the uniaxial strain in a range of stress in which Hooke's law holds. As we all know, Hooke's law states that extension is directly proportional to the load applied. With that in mind, the aim of the experiment we're going to perform today is to observe the tensile behavior of a copper wire and to also calculate and measure Young's modulus of that wire. So let's check out our equipment.
We will need a length of wire, a G-clamp, a meter ruler, a single pulley, 2 wooden blocks, a mass hanger and 100-gram slotted masses, a micrometer which we will use to calculate the cross-sectional area, some adhesive tape and some scissors.
Now for this experiment, guys, we're going to adopt our safety goggles to ensure that we prevent any possible injury that might occur as the wire snaps.
My eyes, the goggles do nothing.
We will also need a tray of packaging material to catch the falling weights and to prevent any damage to the floor.
We have our apparatus set up and we're ready to go. First thing we need to do is, using our micrometer, we're going to measure the cross-sectional area of our copper wire. And these are used widely for the precise measurements of small distances, often in engineering. What we're going to do, take a point on the wire, measure its diameter, and make a note of that. So you want to do this 3 times so we can take an average measurement. So, pick a different location and record again. Now once that's done, you're going to calculate the cross-sectional area of the wire using the formula A equals pi r squared, as you should know from GCSE mathematics. As you can see, we've got our apparatus set up. We have a copper wire clamped between 2 wooden blocks, hung over a pulley held taut by a weight of 1 newton.
With the adhesive tape, make a triangular marker attached to the wire. We then want to measure and take a note of the length from the marker to the clamp.
What we're going to do is we're going to add additional masses to the pulley at increments of 100 grams or 1 newton, and we're going to measure the extension of the wire. To calculate that extension, we're going to record the distance that our triangular tape moves as the weights are applied. So we're going to slowly increase the load on the wire at increments of 100 grams, recording any extension that may occur. And we're going to continue to do this increasing the weight on the wire. Continuing to add the weights until the cable snaps. Now remember before starting calculations that 1 millimeter squared is equal to 10 to the minus 6 meters squared, and that all measurements must be taken in the same unit. Using the calculations and information we've collated in our table, obtaining stress calculated by dividing the mass or load applied by the cross-sectional area of the wire, and strain values. Strain obtained by dividing the extension of the wire by the original length, that is the distance between the marker and the clamp. We can enter them into our equation and calculate Young's modulus of a copper wire. By plotting a graph of stress on the y-axis against strain on the x-axis, we should see that both actions are directly proportional to each other. The gradient of this line can be calculated by dividing stress by strain, as by our equation, giving us Young's modulus of this wire. And there we are. We've been able to successfully calculate Young's modulus of this copper wire. Some things we should note though. Young's modulus is completely independent of dimensions of the material, therefore it will remain the same no matter what the cross-sectional area of the material is. It would be fairly obvious that a larger force would be needed to produce the same extension on a material of larger cross-sectional area. The Young's modulus is incredibly important value as it's a definitive characteristic of a material. It is very important in building and engineering work, for example suspension bridges. I'm not sure about yourselves, but I would like to know what weight the cables on my suspension bridge could hold before I open the bridge to the public, or something like this might happen.